You want to say hi? No, you don't like this, do you? Okay. All right, why don't we get started? Welcome back. So today's lesson, we're looking at a new approach to lists. So we've built a list. We've built our own list that conforms to this fairly basic interface that we set up. It essentially means that a list has to be able to do 5 things, right? So I have to be able to get and set things by index. And then I also have to be able to add and remove elements. So we've implemented that completely using an array to store the values. And now what we're going to do is we're going to explore a different approach. That approach uses linkage. This approach, rather than storing the information about where the items are in the list in an array, we're going to create a chain of items. And we're going to the chain is going to kind of store the location of items in the list. So, in an array, when we needed to look up a particular item, we use the arrays. Array already has this notion of ordering built into it, and so we just use the index that was built right into the array. When we use a linked list, what we do, and we can look at, start looking at the code for this. If I can open it up, yeah. So the linked list class, and let me actually pull this into a larger editor, yeah. So the linked list class contains this inner class. So this is one of the new things that we introduce in today's lesson, is this notion of an inner class. This inner class is located inside our definition of the simple linked list, because the simple linked list class is the only class that's going to use this class, this inner class item. And it's also a class that we should not expose to the outside world. So nobody that uses, remember this abstraction barrier we set up with our interface? So from the perspective of the user of this list, this interface is the only way that they interact with our list. So they can get, set, remove, add, and call size. And as long as those things perform as expected, right? And normally we'd have more documentation in here, right? The idea is that if I call set, the next get at the same index should return the new value. If I call add, there's semantics that we're kind of taking as given, about what happens to the list. So if I add somewhere, the item that I add becomes that index, and everything past that point in the list gets shifted. When I remove, something similar happens, except things get shifted in a different direction, whatever. So there's semantics associated with this list interface. And as long as my simple linked list implementation obeys those semantics, nobody should care how I'm doing things internally, right? Whether or not I'm using an array or, in this case, a linkage. So I've got this private class item, and the way to think about this is that every item in the list only knows one thing. Well, it knows two things on some level. It knows the reference to the value that's stored at that position. That's the same reference that we would have stored in the array previously. And it also knows how to find the next item in the list if there is such an item. So, if I'm at a point in the list where there's still more items after me, my next reference will lead to the next item in the list. So I don't know, you'll notice that the item class has no index. It doesn't actually know what index it's at. It knows where the next item in the list is. So the analogy I like to use for this is kind of like, it's sort of like a kind of like a phone tree almost, right? I mean, even I'm young enough that I didn't hear about this a lot, but it used to be in the past, before the days of email. You guys may find this amusing to hear about. If so pre-email, in a pre-email world, before email was widespread, if you needed to get the word out to a lot of people about something, that was hard to do, right? Because it was like, okay, let's say that, I used to be in an orchestra. It's like orchestra practices canceled today because of bad weather. How do you find out about that? And so what people used to do, and this isn't a perfect analogy, is you would set up like a system where one person would call one person, and then that person would call another person, and that person would call another person. Actually, the way you would do this is actually the first person would call like 8 other people, and each one of those 8 people would call 8 more people, and so it would grow sort of exponentially. This is why they called it a tree, right? But this was a way, so, if I had like, several hundred people that I needed to find out about something, it would take too long for one person to make all those phone calls. People wouldn't find out in time. So rather than doing that, they'd just have the person call a smaller group of people and have those people each call a certain group of people. You had to set this up beforehand, right? At this point, I don't know why I'm talking about this, because it's not even that great of an analogy. But anyway, so with the list, every item only knows what the next item in the list is. And so you could set up a phone tree this way. It would still be very slow. But the idea would be every person would only have to make one call, rather than having to call the entire group. So every item in the list knows what the next item is, and it knows the value at that position, and that's it. And it turns out that just using those 2 pieces of information, we can actually build something that fully conforms or fully implements that simple list interface, right? That can behave like a list. It can set and get and add and remove, just like we did when we built on top of an array, except there's no array here at all. All right, so any questions about this as we get started? I think today's another day where it'd be just kind of good to take some questions and get a sense of. So in the lesson walkthrough, we go through. So in order to bootstrap this, we end up with a kind of a small problem here, which is that when we had an array list, it was quite easy to get started by passing in an array, because the array list already stored items in an array, and so all I did was just copy the array reference and I was done. With a linked list, it's a little trickier, because to get started, like I do want to be able to build a list so that I can experiment with things like get and set, but how do I do that if I don't have any of the, essentially my constructor is going to be passed an array, because that's a common linear data structure that I would use outside of this. So I want to be able to initialize the list from the array, but how do I do that when most of the features don't work yet? And so what we did here is we implement a special case of add, which is adding to the front of the list. So you'll see that my add implementation is only completed if I'm calling add with index 0. That's the only add that I support at this point. The reason that there's 2 reasons to do this. One is that this allows me to bootstrap my list, because now my constructor can actually go through the array and add everything, so that I end up with a list with all the elements in it that was passed to the constructor in the array. It's also because this is a very simple case of add. You guys will finish either add or remove for tomorrow's homework, but The simple case of add is quite simple, where I'm adding to the front of the list. And this is one of these lines of code that is harder to understand than it looks. And we got to go back to thinking about how assignment works. I start on the right, I move to the left. I have some diagrams that we used in the lesson to go through exactly kind of how this works and what references point to what at various points and stuff like that. But this has the effect, you can see that I'm creating a new item, which makes sense because in add, I definitely need to create a new item. Every value in the list is stored in an item. But how this ends up at the front and how the references work and stuff like that is just a little bit tricky. So this is something that we can talk about. At that point, my constructor can actually work because it turns out even just adding to the front of the list is sufficient to be able to initialize using an array. The only trick here is that I go through the array backwards. So I flip the array around and I add from the back to the front. And because I'm adding to the front of the list every time, the items end up in the correct order. So this is how I get my constructor working. And then we go through and we talk about how to walk the list using this. And this is one of these. Let me just sort of jump ahead a little bit here. We'll be quiet. This is one of these sort of canonical for loops. It's a different canonical for loop. This is a reference walking canonical for loop. It's not a array indexing for loop. I would say again, by far the most common for loop is the array indexing for loop. But I would say that this reference walking for loop is probably just about as common. I didn't mean to say that. What I meant to say is that this is also common in certain contexts, right? This is another one of these loops that I look at. I'm like, oh, I've written this loop a bunch of times, particularly when using kind of lower level languages that tend to use things like linked lists. But this is a list that walks. This is a loop that walks a linked list. It doesn't increment anything. It doesn't. The variable that's my loop variable is not an int. And instead, what I'm doing is I'm starting at the front of the list, and my update call is actually moving me to the next item. And I stop when I walk off the list. So when I get to the end, at some point in the list, there is a value that's null. That indicates that that's the last item in the list. When I get to that item, I stop. So this is what allows me, this loop walks the list to a particular position. And eventually, we'll actually factor this out as a private helper function because we're going to need this in a couple of places. But for now, it's just part of our get method. I can walk the list to a specific, I could walk it looking for a particular value. If I wanted to do a search in the list, I could do that way. Usually for our helper function, we walk it to a particular location, right? So I say, I want to get to this index. Okay, so I mean, that's pretty much the content of today's lesson. I'll open the floor for questions for a couple of minutes. What you call this where every node points to multiple nodes? A tree? Yeah, I mean, we'll get to trees. We're going to talk about them later in the class. on some level, yeah. So it's kind of like, let me draw another picture, right? I've even got some paper here right by my computer now for all this picture. No, I'm gonna get a whiteboard soon. This is wasteful, but yeah. So on some level, kind of our lists look like this, right? You know, this is kind of what our linked list looks like. Whoop. This paper got wet. It's weird. So here's our linked list, kind of in diagram form. Make sure this is visible. Oh, there it is. Look at that. It's a linked list. And so the question is, you know, if each one of these links to multiple other items, and I'll kind of give you a sense of what that might look like. So here's an example where every item links to at most 2 items. So this is actually starting to look like something that is called a tree, which we'll talk about later in the class. Now, typically what we'll do when we get to trees is we'll flip this around. So rather than having the nodes maintain the link to the nodes below them, we'll have every node maintain a link to a reference to the node above it, to its parent. This works out better when we talk about trees, because even though a node in this tree can have 2 children, 2 nodes that it links to, every node only has 1 parent. And so creating the data structure is easier when we store the parent node rather than having the children nodes stored at each node. That creates some complications for certain things, but we'll see how to address them. But yeah. Wait, sorry. No. So I'm wrong about that. So what we'll do is we'll actually have every node store the 2 references to its children, either the right or left child. And I haven't thought about trees for a while, clearly. So we'll get there. There is a name for that, and it's called a tree. Now, you know, there's a whole family of these type of data structures that we're starting to kind of peek our way into, right? So in some sense, a list is a special case of a tree, which is a special case of a graph. A graph is probably the most general purpose instantiation of this, right? So a tree is a graph with some extra restrictions. A list is a tree with some extra restrictions. And so the most general sort of form of all of these is a graph, right? And then you get to trees and to lists by adding rules, right? Like, for example, in a binary tree, which is the one that we'll talk about later, every node can have up to 2 children. And the links only go one direction, right? So I can't have a link back to somewhere else in the tree. I can't have a node that has a reference back up to the top of the tree. At that point, it becomes a graph. So a tree is, you know, a graph that has essentially no cycles in it. A list is a tree where every node has just 1 descendant. And so, yeah, so there is this very general data structure hiding in here, right? And we'll kind of get to it. We may talk a little bit about graphs this semester. I think we might have some time. They're fun. There's some really neat algorithms that you can write on top of them. And so, yeah, a multi-headed list really starts to become either kind of a tree or a graph, depending on what what the other rules are about where the references can go. So, for example, here, you know, let's add another. So, for example, if this node can have a reference to a node that's above it in the sort of backwards in the list, now I have a cycle. Now I'm talking about something called a graph. That is just a general purpose graph. How do you find it? So it's a great question, right? So how do we find something? Let's look at the code to do that. Yeah. And I mean, so here's the code, and we'll talk about how this works, right? Keep in mind, this instance of the list only stores a reference to 1 item. So all I know is where the start of the list is, right? I don't know where any of the other items are. So the question is, how do I find those other items? And the answer is, I start at the start and I just move forward 1 at a time using the next reference. Every item has a next reference that tells me where to find the next item. And so what I do is I just walk forward through the list. So you can think about, if we were together in a large auditorium, I would use this analogy of, linking students together. One way is to have you sit down in a row together all side by side. That's kind of like an array list, right? If I need to insert somebody, a bunch of you have to get up, slide over, somebody sits down. But the idea is your position in that row determines your position in the list. A linked list is as if I gave a bunch of you pieces of paper with the name of one other student on it, right? That's the next student in the list. So I need to know who the first student in the list is, right? So I have a piece of paper with somebody's name on it. And so to walk the list, what I would do is I'd be like, call out their name, find them, and I was like, okay, who's the person on your piece of paper? And then I would use that name to find them, and I would say, who's the person on your piece of paper? I would use that name to find the next person. I just keep going. And as I'm going, I'm counting, right? That's the other thing. If you look at this, this loop, it's also counting as it goes. It keeps an index out here, and it bumps it every time it goes through. And actually, we could do this in the, remember, I can actually put multiple things in here. This is sort of more advanced loop syntax. But I could do, I think I can do this. See if I can remember how to write this loop. Oh, it doesn't like this. Let's see here. What does it not like about this? There should be a way to do this. Yeah. Let's see, hold on. Here we go. Remind myself how to. Oh, that should work. Oh, maybe they have to be the same type. Oh, that's unfortunate. Let's see here. Multiple. Just try that. I think I actually have the syntax for this proper. Don't know why. Why do they have to be the same type? Here we go. Ah, okay. So I can't declare two different variables with two different types. So I've actually got to keep this outside the loop. Okay, fine. I outsmarted myself. I could put the update, I think, in here, right? So I could do this, I think, and that's fine, right? Oh, am I actually doing the homework? Yeah, that's fine. Okay. Yeah, I could do this. This will compile and run fine. But typically what we're doing is we're just gonna leave it out here. Yeah. So that's how I'm walking the list. I'm essentially using the fact that every item knows what the next item is, and I know where the first item is. So if I wanted to find the fifth item, first thing I do is find the first item. I use the first item's next reference to find the second item. I use the second item's next reference to find the third item. I use the third item's next reference to find the fourth item. And then I use the fourth item's next reference to find the fifth item. Now, obviously, this can fail anywhere along the way, right? Like if I get to an item and it's got next reference null, then I'm stuck, right? I've essentially reached the end of the list. Now, if you look at the code that we wrote to do this, we're also maintaining the size of the list. And we use that to check our index before we start walking. We could also, so it's actually safe not to do this. So for example, we could also just say this. We could not check the upper bound, because what would happen here is that we go and we go and we go, and then we would, if we break out of the list, it means that we got to the end before we found an item that matched the index we were looking for, which meant the index we were looking for was too far, right? So if the index I'm looking for is 4 and my list only has 2 items, I get 0, 1, 2, I break out of the loop and it's like, couldn't find it, right? But I like to, before I write a loop like this, I like to know that the arguments are okay, and so I'm gonna leave this check in here. That's why this assertion is down here, because we've already checked the size up here on line 27, we should never, this loop should never, I should never actually break out of this loop, because I should always find an item with the right index. Yeah. So that's the trick here, right? The trick is, rather than using an array to store the index of everything, I just use one thing to store how to get to the next thing, right? And so if the nth, so essentially, if the nth item in the list knows how to find the nth plus 1, then I can always find any item as long as I know where the first one is, right? The one with index 0. And that's stored in the list itself. I have to store this, right? If I don't know where the beginning of the chain is, I'm sunk. I got to be able to find the first item. But once I find the first item, I just roll forward one at a time using those next references to bring me to the next item in the list. Yeah, it's a good question. Other questions about this? This is different, right? I mean, this is something that this is kind of a new concept. This idea of linkage, right? Using this to set up this type of linear data structure. One of the reasons that we talk about it in this class is because and there are other ways to implement lists and things like this that we could talk about, but I like this particular approach because it shows you how to use references in this way. When you get, and we'll do this again later when we talk about trees, right? But when you get on into later courses, you're going to need to build data structures by creating individual. So essentially, we're building this data structure. In the past, we built a list by using this one thing, just an array. Now what we're doing is we're actually building our data structure out of these smaller item pieces and connecting them together properly. Tomorrow we're going to look at either add or remove. I haven't decided which yet. Those are really interesting, right? Because then I've actually got to do some really fun manipulation within the list itself, right? I find the right spot and then I have to move some references around in order to get the item into the right place. So that's pretty cool. But yeah, great question about. That kind of is the core question here. If you can understand that, then you can understand the rest of it. Other questions? Other questions? I'm sure there are other questions on this stuff. This is a tricky concept. So, how do we rotate a list? Would it be fair to say searching is ON? Yeah. Let's do a search. That's a fun problem. So let me grab. Is that already up here? Yeah, I wish I had a way to make this a little bit bigger. Let's check this out. So we have some code here in our. That's the constructor. So where I want to be is down here. Okay. So this is my list. I've got get working. I don't have set, remove, or add, but that's fine because I can actually run a search without needing those. So let's write a search function on our linked list. It'll be a fun exercise. So so one thing is when we would add a method like this, we might think, is this a method that every type of list should support? And the answer is yes. I mean, I should be able to search a list. And so I could add this directly to my interface, right? And let's do that. We'll say, what's the return type of this? Maybe it's a Boolean, search, and then I'm looking for a particular value. And this is something that every list should be able to support, right? I mean, it was supported differently, right? But I should be able to do this. Okay, so now let's implement this method. It's going to turn out, it's going to look a lot like what we already did. All right, so we'll say public Boolean search object value. And now, so it's a little different than get, because when I did get, I took an index. And so I could check the index against the size. When I do search, I'm taking a value. And so I don't know, the length of the list is sort of unimportant here, right? What I need to do is I need to walk the whole list. But this is a place where what you'll see is that I don't need another index here, right? Okay, so I'm going to do my list walk. So I'm going to take that that piece of code that I used. One thing to notice about this loop is that if start is null, it terminates immediately. So this loop is always safe to use regardless of whether or not the list has any elements. If this is an empty list, then start is null. What'll happen is I'll set current equal to start. I'll check to see if current's not null. It is null. I'll break out of the loop and I'm done. This is another one of these cases. Remember when we did our search kind of patterns on arrays, where what we're doing is we're essentially finding a counterexample. So my default assumption is that the list does not contain this element. And what I'm going to look for as I go through is a counterexample. I need to find an element where the value is actually equal to what I'm looking for. And if that's the case, then I'll return true. So now this is quite straightforward. All I need to do is say if current.value dot equals value. Okay, then return true. Right? So that looks like it would work. Let's try it. Okay, so I'm going to write some additional test cases here. List.search. So I should be able to find you in here. Dot equals true, and I can just say double equals true, right? So that works. One potential complication here that you might have noticed, I have to be careful with null. So there's two cases. First of all, null is a valid thing to put into the list. So it's possible that value is null. But the thing that's more concerning here is if current.value is null. So for example, if I put, let's add a null string here. Now you're going to see I have a null pointer exception. Once again, it's on line 64. And, oh wait, hold on. That's actually, that's because this, okay, so now, oh, sorry, I need to fix my other test cases. So now I've got this null pointer exception in my search method. And the reason is right here, because I haven't checked to see if current.value is equal to null. So what I'm going to do is I'm going to say if current.value is equal to null, and value is equal to null. So it's possible that I'm looking for null, and I found it, or current.value is not equal to null, and current.value equals value. So those are the two cases. Checkstyle is going to be angry with me because I need to put this on a new line. And I think I'm going to need some indentation here. Oh, there we go. Yeah, still mad. Okay, now it's correct. And let's make sure that it also finds null. So if I look for null, this should also be true because null is the first value. Yeah. So, again, let's look at our search and let's try to reason about performance. So I see a loop. So I'm getting suspicious that this is potentially ON. I don't see a nested loop. I see a loop, and then there is a return statement inside the loop. But in general, because of the structure of the list, I don't know whether the item is the beginning of the list or the end of the list. So on average, now the other thing whenever you're searching that plays a role is, do you know whether or not the item's in the list at all? So if I was just searching for random strings in a list of strings, 99.99999% of the time, the value is not in the list, right? Because I'm searching for a random string. So most of the time I'm going to get all the way through the list and not find it, right? So most of the time I'm actually going to finish the list and return false. And so I would say the average case behavior for this function is actually ON, because in the average case it doesn't find the value and gets all the way to the end before it breaks out. Can I do any better? No, right? I mean, if I've got a list, I got to look through. Now that's actually not true. So if I sort, there are some clever things that I can do, and we may go through this at some point. If I sort the list, I can be more intelligent about how I search it, right? So if I sort the list, I can run something called a binary search. This is kind of like the famous phone book example that they do in CS50, right? Think about how you search a phone book, right? You don't search it one page at a time because it's sorted. And so you use information about the relationship between what you're looking for and the other items in the list to determine what to do, right? So, David's example, which is fantastic, is, you open the phone book to the middle, and then you say, is it in the left half or the right half of the book, right? And then you only have to search that other half, so you've made the problem half as small. Then you go to the left side or the right side, you divide that in half, left side or right. So you just keep doing this, and eventually you can narrow it down very, very, very much. But that implies that the list is sorted. That also implies that the items in the list are sortable, which implies comparable, essentially. When we talked about comparable, we said not every item in Java can actually be sorted. There's not a natural order for everything. And so one of the things that you get out of a natural order is you get sorting. If I maintain a sorted list, I can do search faster. But in this case, the list isn't sorted. And so the best I can do for searching is ON, because I really do have to go through every element. And so the runtime for this would be ON, just linear walk through the list. Yeah, great question. Yeah, I feel like at this point someone's asking me like a CS225 MP part of the CS225 MP on lists. Rotation is tricky, right? Rotation requires maintaining some references properly, right? In general, that's a tricky question, right? It's on the CS225 MP for a reason, because it requires some care. But one way to think about it, let's try to kind of walk through. I'm going to draw some pictures here. Right, so here's my list with my, come on, Geoff, you can make a better 3 than that. There we go. You get the, I'll just put this. All right, so here's my list with 5 items. And let's say that I want to rotate, well, this is a little bit of a crappy example because the middle 3 items is going to be a fair amount of work, right? So when I'm done, if I wanted to rotate these middle 3 items, what I want when I'm finished is I want the list to look like this. So I'm going to rotate it to the right, meaning that 4 is going to come over here. 2, 3, 5. Right? So here's my new list. I've rotated the middle 3 elements to the right by 1. So 4 moved around to the beginning position, 2 and 3 moved to the right. And so the trick here is to think about, oops, sorry, you can't see this. The trick here is to think about which references do I actually need to change in order to get this to work. So this reference from 2 to 3, this reference from 2 to 3 does not need to change, right? It's still the same. This reference from 3 to 4 does change because 3 now needs to refer to 5. The reference from 4 to 5 needs to change because 4 needs to refer to 2, and the reference from 1 needs to change. So I counted, let's see here. This one needs to change. This one's okay. This one needs to change. And this one needs to change. 3 references that need to change. The reference of the item right before the rotation, and then the reference of the last item in the list that I'm rotating, and the second to last item. It turns out that if you make this list much larger, like let's say I did this with a list of 60 elements, and I was rotating a section of 20, I still only have to change 3 references. So that's part of the trick behind this problem, right? Is that even if the list gets very long, most of the inner part of this rotated list, the references stay the same. And so the trick is to identify the references I need to change and then change those appropriately. Yeah, I mean that's the trick of doing this particular problem. But again, I mean this I will leave this as an exercise for the reader, particularly once you guys get on to CS225. I'm not gonna spoil your fun with that part of the MP. All right. Other questions about lists? Got the searching. Yeah, searching is ON. Good. Anything else? You can finish up a little bit early today if you guys want. It's beautiful outside. Go outside and spend some time with the cat. She has a little tent that we use that we use for her when she's outside. And she's decided that the falling leaves are sentient, so they need to be attacked when they fall close to her tent. So that's kind of fun to watch. It's definitely trickier than rotate string, right? Now, on the other hand, I mean, one thing you could do here, which would probably be considered, not the way to do it. So think about how we rotated the string, right? There were solutions that use substring, but there's another solution which is essentially load everything into an array and do operations on that array. So one thing you could do here is so given a particular list that's stored using a linked list, I could load it into an array, right? So I could set up an array of object references. I could load the linked list into an array, all the references, and then it might be actually easier to do operations on that array, right? Things like rotations. And then when I'm done, I could take the array and convert it back into a linked list. I suspect when they're asking you to solve problems like this in 225, they're not asking you to do it that way because it's not as much fun. But that would still work, right? And that's sort of, again, what we did with strings, right? We took the string, we convert it to an array of characters, we operate on the array of characters, and then when we're done, we convert that array back into a string. And so you could do the same thing with a list. But yeah, overall, this is the rotations and things like that on lists are a trickier problem because you have to maintain these references. And the other thing about it is that, and we'll talk about this tomorrow when we do add or remove, is that when you operate on a list, remember in Java, if I lose a reference to an object, that object is gone. And in particular in Java, when I'm working with lists, if I lose a reference to a portion of the list, Java will actually delete the rest of the list because nobody has a reference. So for example, if I wanted to clear the list, let's say that I have there actually is a clear, the list interface in Java has a clear method that just removes all the elements. So how would I do that? Given my current implementation using a linked list, it's actually quite straightforward, right? So I could say public void clear start is equal to null, size is equal to 0. That's it. And really most of what I'm doing is right here. It doesn't matter how many items I have in the list, right? Because the only thing that's keeping them around is that start reference. So if I remove the start reference, nobody has a reference to the item with the item at the front of the list. And what Java will realize is, nope, because I can't refer to the first item, I can't refer to the second item or the third item or any of the items in the list. And so they'll all be deleted. And so this is one thing that makes it tricky when we work with lists, is that particularly in Java, is we have to make sure that we keep a reference to the rest of the parts of the list around that we need. Yeah, it's a good question. Other list related questions. I wouldn't do again, I think the array method is sort of cheating. I mean, it is possible to do things that way, but I wouldn't, it creates a lot of extra overhead. And it's probably not the way that they want you to solve the problem. There is a way to do that type of rotation, right? I would probably focus on, if you're really interested in doing this, I would probably focus on rotating the entire list first. That problem is a sort of a less general version of the problem of rotating a part of the list. And I would just do rotation by one, and then I would move on and do larger rotations as needed. Any other questions about lists? Do you have any questions?
No.
Oh, no. Okay. All right. Are we done? You ready to go outside? Beautiful day. All right. If there are no other questions, I think I'm going to let you guys go. If you are in the Champaign area, I would strongly encourage you to go outside. It is a beautiful day. Probably the last, I keep saying this, but you know it's coming. It's winter. It's on its way. There'll be snow on the ground in a few months, maybe sooner. So today it's 80 degrees. I've got shorts on. I would suggest that you go outside. and enjoy the weather because it is not going to last. Tomorrow we're going to wrap up our discussion about lists, and we'll look at sort of some of the trickier methods for linked list construction in terms of operations. And so at this point, you guys are doing get and set. We haven't done add or remove. We've done the simple case of add, but we haven't done remove. And so we'll do one of those tomorrow. We'll talk about kind of how to approach it and how to think about it. The other one will be something for you to work on as a homework problem. And we'll also talk about the performance differences between the two types of lists and why you might want to use one or the other. So I will look forward to seeing you all tomorrow. Enjoy this beautiful day.